Let's talk earthquakes. This is chapter 10 from the Earth textbook. This is going to be split into 4 sections on the YouTube. We're going to do an intro and faults, and then the energy of earthquakes, how that's generated, how it's released, releasing it into seismic waves, measuring it with the seismographs, and then talking about the magnitude or the size of earthquakes, and then plate boundaries and the different plate boundaries where earthquakes are, and then how the energy comes about as damage from an earthquake, and then predicting earthquakes. So that'll be the lecture on earthquakes for chapter 10 from the Earth textbook. The earthquake is a shaking that is a release of energy that is built up during plate tectonics. The energy is going to be released. Usually it's going to be on a fault surface. It's going to release and expand away from that fault rupture. The wave then it moves around the globe. So an earthquake that happens in one place on the globe can be detected in another place on the other side of the earth. They're really common, earthquakes are. They happen every day, all day long, and there are more than a million earthquakes per year that are detectable. And it says here most of the earthquakes are from tectonic motion. That is because there are earthquakes like from the testing of nuclear bombs, things like that. So those are also going to cause earth seismic waves that move through the earth. The images down here along the bottom, you can see kind of foreshadowing, so the earth is going to deform. It's like bending a stick. And if that stick were to break, pop, that release in energy is the earthquake there. Like I was saying, there's more than a million earthquakes, and so most of those are not going to be felt. They're going to be really small. Moving my face around. But the large earthquakes can really topple a city because of the buildings that fall, and because of the falling buildings, people die. So there have been 3.5 million deaths in the last 2,000 years because of earthquakes. The table here on the right then shows at the top, we're starting at 2011. That's the last really big earthquake that had a huge impact, and 20,000 people died in that event. And that was mostly due to the tsunami that occurred. We hear on the news still about the Fukushima nuclear power plant that was destroyed during that earthquake in 2011. As we go back from there, also in 2011 was the earthquake in New Zealand, and then a big earthquake in Haiti, unexpected because Haiti hadn't had an earthquake in a very long time, and so many deaths, 230,000 people died in that. The last big one before that was also 230,000 in 2004, and that was during the tsunami that occurred around Christmas time, Christmas and New Year's in Sumatra. Back before that, the next big one would be a one in 1976 in China, 255,000. And we have to go back again to China in 1927 to get that magnitude. So these 200,000 plus events don't occur very often. Usually you'll see it can be in the thousands or hundreds of people that die in an earthquake event. In the United States, we go back to Northridge in 1994 with 51 people died. And that was mostly from the pancaking of a freeway, 2 bridges on a freeway that pancaked, and a apartment complex that also pancaked. And that's most of the loss of lives were in those 2 places during that event. So most of the damage is really due to the ground shaking, but Yeah, the tsunamis, the one in Japan recently, and not too long ago, the one in Sumatra, the Indonesian earthquake, both caused tsunamis. So, and those can be very, very devastating, and a lot of loss of lives from those two events. So, what causes earthquakes? It's going to be sudden motion along a fault, and that fault can be an existing fault. Can I make this smaller now? I'm just going to scoop myself here. Along an existing fault, it can be a fault that we can break a new fault. So a new fault can occur at an active tectonic setting. There can also be fault motion because magma is moving through the plumbing system of a volcano, and the crust is adapting to new pressures and changes. When a volcano erupts, also the crust can change, and earthquakes can occur. Meteorite impacts, that impact can cause earthquakes. Landslides, if they're big enough, can cause the ground to shake. And then I mentioned before, nuclear detonations. Most of the earthquakes, though, are going to be caused by fault motion. So here is a fault. This is a reverse fault. The hanging wall is going up. Top part of this fault is going up with respect to the footwall, which is on the bottom, and that's a reverse fault. So we have a convergent plate boundary in that spot where one side is going to go up over the other side. There are parts to an earthquake. I'm going to find a place for my face again. I'll just put me right here for now. The focus is down inside the earth where the earthquake is generated. And there's going to be a rupture plane along that fault. And then up above the focus, though, is going to be the epicenter. So the focus is focused down on where the rupture is, and the epicenter is just right above it on the land surface. When we look at a map of earthquake activity, we're looking at the surface, and we're looking at a bunch of epicenters. So the map here on the right, this is Utah, and here's Salt Lake. This is the Basin and Range. There's these north-south trending faults all throughout the Basin and Range. That is the edge butting up next to the Colorado Plateau. So that's just a geological area that's uplifted out in the west. So the middle of Utah is separated with the Colorado Plateau and the Basin and Range. There's faults going throughout the Basin and Range, and there's earthquake activities along those faults. So all those circles represent the epicenter, the trace, the surface expression of those faults. Okay. So this is brittle brittle deformation in the crust. They are planar, so we can like make a plane out of them. They're on the side view, they're linear, so we can draw a line. Most faults are going to be at an angle. So if they were vertical, that would be kind of unusual. So there's usually going to be some little bit of angle to that fault surface. Because of that, then we have, I'm going to turn off my phone. We have a top and a bottom to the fault. And the top part over here, this is the hanging wall. And then the bottom of the fault, so if it's at an angle, the top of it's the hanging wall, the bottom is the footwall. That doesn't, so then we can talk about motion along that fault as if the hanging wall is moving up or the hanging wall is moving down. So see this little person in here? That's showing a person, and see their feet? Their feet are in the footwall. So let's zoom in on that. Oh, move my face out of the way. I made that person a little bit bigger. So their feet down here are in the footwall, and their head is in the hanging wall. They like to say, like if you were in a tunnel and you had to hang up your lantern, you were hanging it up on the hanging wall. So that's above the fault. Hanging wall, footwall. The fault motion then, or the classification of faults, is done by where's the hanging wall going. So if the hanging wall is moving down, then that is a normal fault. So normal fault, hanging wall is moving down with respect to the footwall. And the reason this is happening is somewhere in the crust there's extension, like a divergent plate boundary. So in that extension, right, one part's going to move down with respect to the other part. If you have squeezing or shortening or compression, then you're going to have a reverse fault. And in that case, in this image, the hanging wall is moving up with respect to the footwall. The angle there of the fault is called the dip. So this would be horizontal, and the example here is dipping at 60 degrees. So the movement is along that dipped surface. It's dipping down 60 degrees, and the hanging wall is moving up with respect to the footwall. If you take that fault surface, instead of 60 degrees, we shallow it up to about 30 degrees, then we have what's called a reverse fault. This is a thrust fault. This is a special kind of reverse fault. It just means that the fault plane is a low angle. So a low angle means that hanging wall can slide a long ways at that low angle. So that happens a lot when we have mountain building, when we have a convergent plate boundary and two pieces of continental crust are hitting each other and ride up over each other, like the Appalachian Mountains or the Himalayan Mountains. The third kind of fault is a strike-slip fault, and in this case, so the fault plane is vertical, and you have two pieces of crust, and they're going to slide side by side. So the other ones were sliding along some kind of dipped surface. In this case, it's vertical, and the chunks of crust slide side by side. That's a strike-slip fault. The movement along the faults, we call that displacement. So we're displacing rocks as they slide side by side. In this image here, this fence was once a continuous fence, and now it's offset by some amount of space, and that offset we call displacement. So the fault, we can draw it between those two lines of fencing. So over here, what a geologist sees, the fault is along the ground here. Those arrows are going to represent the fault motion. So as I'm standing over here and I'm looking over at the other fence, this line of fencing here, it's moving to the right. So we would call this a right lateral strike-slip fault. So I'm looking across at the other side. This fence has moved to the right, right lateral strike-slip fault. Okay. Move my face again. So faults are everywhere at plate boundaries, and we can see them sometimes. You can see the fault going across the image here, and those will be active faults that we can see. There also can be faults that are not active from our geologic past. So I'm in Boone, Appalachian State's in Boone. There are faults here in the Appalachian Mountains. I can go out and I can put my hand on those faults, but they're not active anymore. They're at plate boundaries where there's no plate motion towards or apart or side by side, so they're inactive faults. So we have sometimes earthquakes, but we don't have active tectonics along those faults. So this fault trace here on the image is showing that fault motion along that. There's a road here. It looks like it would continue, it stops, it's offset, and then the road of a jeep trail continues again. There can be faults in the subsurface that we don't see because there's no surface expression, and those would be called blind faults. So blind faults also occur in areas that are tectonically active. We just sometimes can't see those faults.